This video deals with the preparation and reactions of amides. Amides have the general structure shown here with a carbonyl attached to a nitrogen either bearing hydrogens or some number of R groups. We saw in the previous sections that acyl halides, anhydrides, carboxylic acids, and esters can all be used to generate amides through a nucleophilic acyl substitution reaction. The best of these four options is the acyl halide because the leaving group is the best of all four of the reactions shown on this slide, and the byproduct generated is easily removed by extraction or other purification methods, unlike the anhydride example, which produces a carboxylate anion, which sometimes can be a little harder to remove from the reaction mixture later on. Carboxylic acids and esters are really slow reactions to produce amides and therefore not desirable. Amides can react under acidic or basic conditions to produce either a carboxylate if we're under basic conditions or a carboxylic acid under acidic conditions. However, this reaction is really slow because the amide nitrogen containing group is a really poor leaving group, and we learned earlier that amide carbonyls are the least electrophilic of all the carbonyls because the nitrogen is able to serve as a really good resonance donor of its lone pair electrons toward that carbon. So trying to do any nucleophilic acyl substitution reactions on an amide is difficult and often is a slow reaction and requires prolonged heating like the ones shown here. So generally amides aren't used in these sorts of reactions simply because of the two factors mentioned here, poor leaving group and least electrophilic carbonyl. There is an exception in which amides are useful in biochemistry in nucleophilic acyl substitution reactions, and that is with penicillins. Penicillins have the basic structure shown here, which is referred to as a beta-lactam when the amide is in a ring like this. Off of this carbonyl is an R group that's variable depending on the penicillin. So in penicillin G there's a benzyl group. In amoxicillin there's another benzyl group that's substituted in two positions. Beta-lactams are susceptible to reaction with water to form the carboxylic acid. And the reason they're more susceptible to doing the reaction that was on the previous slide is because of the ring strain. Because this is a small four-membered ring, there's a lot of ring strain in it, and that makes the nucleophilic acyl substitution more favorable, or that ring opening more favorable. It makes this nitrogen a better leaving group. As you may know, penicillins are used as antibiotics, and the reason they're successful in many cases is that there's a bacterial enzyme referred to as transpeptidase that helps facilitate the hydrolysis of beta-lactams and the substitution of an OH in this position. After it facilitates that hydrolysis, the enzyme becomes inactivated, and it turns out that inactivated transpeptidases can no longer promote bacterial cell wall formation. So that's how penicillins act as antibiotics, is they prevent future formation of bacterial cell walls. There are certain bacteria that have become antibiotic resistant, and the reason for that is that there's a different enzyme, a competing enzyme, that will hydrolyze the penicillins, or the beta-lactams, and that leaves the transpeptidase in its active form, which will allow it to continue producing bacterial cell walls. We will look at one reaction of amides that is successful, and that is the reduction of amides using lithium aluminum hydride. This reaction looks a little bit different than most of the reductions we've seen with lithium aluminum hydride, because in most of those reductions we saw the formation of an alcohol in which this oxygen was retained and subsequently protonated by water. But in this case we see that the oxygen is removed completely, the carbon is reduced, it gains 2 new carbon-hydrogen bonds, and the nitrogen of the amide is what gets protonated by the water. So let's look at the mechanism for this and why it is that the oxygen is lost. So like other reactions with lithium aluminum hydride, the aluminum hydride serves as a hydride source or a nucleophilic H- source. So that nucleophilic H can react with the carbonyl carbon, pushing electrons up onto the oxygen to form the tetrahedral intermediate, which is electron rich at this oxygen. The byproduct AlH3 has an electron deficient aluminum. It has an incomplete octet, which therefore can act as a Lewis acid and accept a lone pair of electrons from this Lewis basic oxygen, forming a new sigma bond. This aluminum species is reactive just like the aluminum hydride in that it can serve the role as either a base or as a nucleophilic hydride source. And in this case, it's in very close proximity to this hydrogen. And so that nucleophilic hydrogen can grab the hydrogen off of the nitrogen, forming H2 gas. So entropically, this is very favorable, forming a nice stable gas molecule. The electrons in this nitrogen-hydrogen bond can then move over to form a pi bond between the carbon and nitrogen, kicking off the oxygen as a leaving group. So it's in this step that we've lost the oxygen and formed an imine. This imine can then react with another equivalent of lithium aluminum hydride because it is again electrophilic at this carbonyl. And when that equivalent reacts, we form a tetrahedral intermediate, but instead of having an oxygen here, we have a negative nitrogen, which can be protonated by the subsequent addition of water, forming this amine.